Okay, we're going to close these principles with a little bit more math. The language of physics is math, and we're going to work out the electric potential of a point charge. Just one concept in this section. It shouldn't take us too long. We're going to state the electric potential of a point charge, and guess what? Here it is. It's kq over r. You might say, well, it looks a little similar to Coulomb's law. And I would say, good call, because that's where it comes from. Coulomb's law has to do, as you might remember, with the force between 2 point charges. And also, from Coulomb's law, we got the electric field produced by a single point charge at a distance r away from that charge. If you might remember, that the electric field produced by a point charge q, a distance r away from that point charge, its magnitude is given by kq over r squared. So in order to understand this, electric potential of a point charge, it's helpful for us to review concept 4 in this same chapter. State 2 rules of thumb for the electric potential. The electric potential is high near positive charges and low near negative charges. Before we say that, you can derive this result from this. They look similar. There's a K, the Coulomb force constant. There's a Q, the charge. There's an R squared in this case, but an R in this case. However, it requires the calculus, and so the derivation is a little bit painful. I believe it's done in the book. Actually, I think it is not done in the book. The book actually uses no calculus. So just take my word for it that you can derive this with calculus. But the bottom line is that potential of a point charge, a distance r away from it, is V. So let me say what that means. If we have a point charge Q here, and we're interested, I want the electric potential here. I want it at this spot. There might be something there, there might be nothing there, but I'm just interested in what the electric potential is. Well, what is it? It's kq over r, where k is at 8.99 times 10 to the 9. Q is the charge itself in coulombs, and r is the distance to the point we're interested in. So let's see if this is consistent with the rules of thumb for electric potentials. The electric potential is high near positive charges and low near negative charges. All right. Let's take a look at that. If this charge is positive, then, and if we're near the positive charge, okay, so in that case, r isn't way out here. R is really small. So the distance between the charge and the point where I want the electric potential is small. Well, r is small, and if r is small, since we're dividing by r, and you're getting something that's really small in the denominator, what does that do to the quantity itself? Well, it gets big. In fact, the absurd limit is where r goes to 0, and that would be the electric potential is kq over 0, and that would blow up to infinity. So the smaller r gets, the bigger V gets. And so that implies that V is large and positive near a positive charge. So what to think about here is that this is like a mountaintop, really high spiky mountaintop. If the charge is positive, Q is positive, V is positive, and it's huge near that positive charge. So the electric potential is high near positive charges. Is that true? It sure is. It's like we've just shown it. Is it low near negative charges? Well, what if this charge is negative? So we got a negative charge here, and I'm interested in the electric potential a distance r away from that negative charge. And let's say r is pretty small. If the charge is negative, Q is less than 0. It's a negative number, right? So that Q will be less than 0, and if Q is less than 0, that implies that the electric potential must also be less than 0. And that says that that's consistent with the fact that the electric potential is low. In fact, it's negative near negative charges. All right, and then the electric force pushes positive charges toward lower electric potentials and negative charges toward higher electric potentials. So, see if I want to get anything out of this. Okay, this diagram here, don't know if you can see it very well. You should be able to see it more or less through my scribblings. This is for a positive test charge, okay? And it's a plot of the potential, V, as a function of distance away from this positive test charge. As we get closer and closer to the test charge, so as we get closer and closer to that test charge, as we're moving along this axis here, R is decreasing, getting smaller and smaller. As R gets smaller, V gets bigger. And so that's exactly what we're seeing here. This vertical axis here measures the electric potential. So as R gets smaller and smaller, the electric potential gets bigger and bigger. And in fact, when R goes all the way down to 0 and we're right butted up against that charge, we're sitting on the charge, then the electric potential goes to infinity. So great, I think I beat that one to death. The potential of a point charge. All right, let's do a quick example. This one's not very complicated. Determine the potential 1.2 meters away from a point charge. And this is the charge, this is the distance, when the charge is positive and when the charge is negative. This is just plugging in numbers, so it's no big deal. V is KQ over R, happy day. We know what K is, we know what Q is, it's given up there, 4 times 10 to the minus 8 coulombs, divided by the distance of 1.2 meters. So this is for the positive charge. And if we plug in for a negative charge, change this positive to a negative, then obviously we're just going to get the negative. So, pretty simple example. 4 point charges are individually brought from infinity and are placed in the corners of a square. 1, 2, 3, 4 charges. Each charge has the identical value of plus Q. The length of the diagonal is 2a. So between here and here is 2 times a. So it'll be a from here to there and a from the center to the other one for a total distance of 2a. What's the electric potential at P at the center of the square? Well, good question. How are we going to do it? We know how to deal with one charge, that the potential due to one charge is kq over r. But what about four charges? So we're interested in the potential at this point P. I want the potential, electric potential, here. And I encourage you, when you're thinking through these problems, to do exactly what I've done right here. Just so you don't get confused, you know what you're looking for, what you want, and where it is that you want the electric potential. But the electric potential at this point here is going to be affected by the four different charges. So let's do them one at a time. Let's do this guy. The potential here is K. So the charge itself is denoted by capital Q instead of lowercase q. Still means charge, no problem. If we're just forgetting about this, forgetting about 1, 2, 3 charges, and we're just worried about this one, then what's the potential going to be? Well, it's K times the charge itself, this one here, divided by the distance between the charge and the place where I want the potential. What's that difference? Distance. It's A. No problem. But just like electric fields are additive to get the net electric field, electric potentials are also additive. So you add up all the potentials due to all the charges, and that gives you the total electric potential. So let's add in the electric potential due to this guy. Well, what's he going to be? K, Q, divided by the distance between this charge and this point. What's that distance? A. And you're starting to see the pattern here. For that one, it's going to be KQ over A. And for this one, KQ over A. Plus, that's a plus, not an equals, KQ over A. And what do we get? We get four terms that add together to give 4KQ over A. So here's the answer. Now, you might say, well, wait a second here, Dr. Edwards. This is kind of interesting, because when we dealt with electric fields, we always had to take the direction into account. And the one example that we did where we had charges at different corners of a rectangle, and sometimes the electric fields canceled each other, and we had to take the direction into account with electric fields. I say, you're absolutely right. That is true for electric fields. We have to take the direction into account, where those come from. With electric potential, not so. You just add them up. You don't have to worry about where they are. I mean, you could have had a fifth one at a distance A right here, and it would have just added another identical term onto this list. That's it. The only thing you do have to keep track of, though, is if had one of these charges, for example, been negative. So suppose this one had been negative, a minus Q. Then what would you have done? Well, then you would have put in a minus Q here. And so then that one would have canceled one of these other terms. But you don't have to worry about direction with electric potential. At locations A and B, find the total electric potential. This one is another very similar problem. We attack it in exactly the same way that we did the last one. So let's look at location A and try and find the total electric potential. Well, at point A, this is where remember, I want the electric potential here. How am I going to find it? I've got two charges, a positive one, 8 times 10 to the minus 9 coulombs, and a negative one, negative 8 times 10 to the minus 9 coulombs. And I might ask you, which one will play the bigger role in determining the electric potential? Will it be this positive one or this negative one? And you say, and I think you will, should be probably the positive one will play a bigger role, because the distance between where I want the potential and that charge is smaller, so R is going to be smaller, so V is going to be bigger. It's going to play a bigger role. All right, let's actually plug it in and see if that's actually true. Here's KQ over R. KQ over R for this charge. Now, what did I use for R? R is the distance between the charge and the place where I want the potential. What's that distance between the charge and where I want the potential? 0.2 meters. So that's why I use 0.2 meters here. Plus, we have to add in the potential for all the other charges. Remember, always put a plus sign here. You never have to think about minus signs or directions or anything. Just put a plus sign in, and everything will be happy. Here's K. Here's a charge, and that's where the minus sign comes in. You plug in the value of the charge, whatever it is, with its positive or its negative sign, and everything else will take care of itself. Divided by 0.6. Well, how did I get 0.6? That's the distance between this negative charge and the place where I want the potential. And what is that distance? And you say, well, easy. 0.2 meters plus 0.4 meters is 0.6 meters. So at the end of the day, we end up with a potential of 240 volts. Is that positive or negative? You say, that's positive. Should it be positive? We know that the potential is positive near positive charges. And the potential is negative near negative charges. We're closer to the positive than the negative. It has a bigger role. The potential is positive. Perfect. What about at point B? And you say, well, I'm starting to get the idea here, Dr. Edwards, because if we do for point B and I want the potential here now, then I just plug in, I'm going to need 0.4 for R for this distance, and I'm also going to need 0.4 for this distance. Everything else is the same. And both of those terms look identical to each other except for this minus sign. Therefore, they cancel each other. So right here, halfway between, the potential is 0 volts. Here it's 240 volts. What is it here? You say it's going to be bigger than 240 volts, and you would be right. Maybe 1,000 volts or whatever. As I proceed over this other direction, what if I put a what if I was interested in the potential right here, point, say, C? You'd say, well, by symmetry, looks like it's probably minus 240 volts. And then if I'm over here, closer to here, it'll be even further negative. Yeah, you get the idea.